Hi everyone, this is Dr. N.V. Suresh Kumar, Assistant Professor, Department of Physics. Here I am going to give a lecture series on essentials for quantum computing. Today's topic is bits and qubits, lecture 1. So in this presentation, I am going to explain what is computing and also bits versus states and qubits versus states. Through this presentation, we understand the advantages of quantum computing. See, computing means we use computers to solve complex problems. So in this process, we give some input data to computer and there are some algorithms, some set of rules, they apply on the data and they process the information and gives you a solution to the problem. So computing is of two types. Whatever the computer that we are using currently is called classical computer, because while processing the information, it uses laws of classical physics. That means in processing the information, first these computers will convert the data into bits. A bit is a definite state. It may be bit, we call them as state 0 and state 1. That means any information that you have given to the computer is converted into binary states, that is either in the form of zeros and ones. This is binary information. That is, we have two states, 0 or 1. So converting the information in the form of bits and processing it, giving the solution is all called as classical computing. On the other hand, there is another way of doing this computing, that is quantum computing. In this quantum computing, we convert the data into qubits. A qubit is a superposition of two states. The states are 0 and 1. So we say that a qubit can exist either in 0 state, 1 state, or 0 and 1 state simultaneously. That is superposition of 0 and 1. So this gives you some power to the computing. We understand this. How qubit, which is in the superposition of state 0 and state 1, gives a power to the computing. So for example, you see here is a picture here. I just want to see what is 0 state, what is 1 state practically. So for example, here you see this one. I have two energy states. Let us call these are energy states of electrons. Say two states. Say electron is in the lower energy state. Say this is lower energy state, this is higher energy state. If electron is in the lower energy state, then I use this state to represent bit 0. Similarly, if the electron is in the higher energy state, I represent this state as bit 1 or state 1. Okay, that means when I say the information is converted into state 0 and state 1, and the physical representation of those states is in the form of electronic states. Electron in the ground state represents bit 0. Electron is in the excited state represents bit 1. So we can understand this easily. Now see this qubit. What did I say? Qubit lives in two states simultaneously. That is, a qubit will stay in state 0 and state 1 simultaneously. So this is what we need to understand now. A quantum particle can have an ability to stay in both the states simultaneously. Electron is a quantum particle. So we can have a state where an electron is living in both ground state and excited state simultaneously. We consider this as qubit. Okay, so let us start understanding how this qubit is used in processing the information, and this is giving a power to the computing. We will understand this now. So I already said qubit is a superposition of two states. Let us see this one. Let us start with classical computing first. So I already said that in classical computing, we represent the data in the form of bits. Let us see this one. Say for example, I have one bit. I have one bit. This bit 1 can be in two states. That means it may be in state 0 or state 1. But you can't find a bit staying in both the states simultaneously. That is the point we need to understand. Say for example, I have 2 bits. Using 2 bits, we can generate 4 states. What are those 4 states? 0, 0, 0, 1, 1, 0, and 1, 1. Let us come to 3 bits case. If I have 3 bits, how many states I can generate? 8 states I can generate. You see here, this is a bit strings of bit length 3. 0, 0, 0 is one state. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, and 1, 1, 1. 8 states I can generate using 3 bits. If I continue like this, in general I can say that if I have n states, you can generate 2 to the power of n states. You can see this one. You can write 2 as 2 power 1, this 4 as 2 square, this 8 as 2 cube. So if I have 3 bits, I have 2 to the power of 3 states. If I have 2 bits, I have 2 to the power of 2 number of states. If I have 1 bit, I can have 2 to the power of 1 number of states. These are the states. So if you continue like that, if I have n number of bits, I will have 2 to the power of n number of states. So every state is of bit length n. So these are all the states. Now the point is that even though I have 4 states, I can generate only one state at a time. Right? So that is the point we need to understand here in classical computing. Now that is using 2 bits. Now next point, I have a question. Using 2 bits, if I want to generate 4 states simultaneously, what to do? See, I said that if I have 2 bits, I can generate either 0, 0 state, 0, 1 state, 1, 0 state, or 1, 1 state, one at a time. But what is the question now? I want to see all these 4 states at a time. Then what should I do? Now the answer is that now you use 4 circuits, classical circuits. Say classical circuit A, giving you the state 0, 0. Another classical circuit B, generating the state 0, 1. Another classical circuit C, giving you the state 0, 1. Next classical circuit D, giving you the state 1, 1. So now I have to use 4 circuits, 4 different circuits, each one generating one state. So using 4 circuits, I can generate 4 states simultaneously in classical computing. So now let us generalize this. Now what did I say in the previous slide? If I have n number of bits, I can generate 2 to the power of n number of states. Now take log on both sides. Log n base 2 will become log 2 power 1 base 2. This is equal to n. Now what is the point here? The conclusion is that if I want to see n states at a time, how many bits I require? N into log n base 2. See why this n is coming here? I already said that. See, if you see this slide again, if you want 4 states, if you have 4 states, for each state you need a circuit, one circuit. So 4 states, 4 circuits. N number of states you want to generate simultaneously, then you should have n circuits. So the point is that if you want to generate, see, if you want to generate n states, you need log n base 2 number of bits. But all these number of states are not generated simultaneously. One at a time only. But if I want to see all these n states at a time, I need n number of circuits. So I multiplied this number of bits log n base 2 with n. So if I have n log n base 2 bits, I can see all n number of states at a time. Okay, remember this point. Now let us see graphical representation of this function. What is this? Here I have taken number of states along x-axis, number of bits along y-axis. Okay, now see that this is the product of two functions. The number of bits you require for generation of n states at a time is product of two functions, n and log n base 2. So now see that this is product of two functions. So I have two representations here. The first line, this is linearly, this n indicates that as number of states you want more, the number of bits n increase linearly. Next one is logarithmic function. As number of states that you want to generate increases, this part increases logarithmically. Okay, now if the number of states what you want to generate is very high, your linear function dominates the logarithmic function. That means, what is the point here? The number of bits required increase linearly with the number of states if the number of states required to be generated is very large. Okay, this is very important point. We will see this point again at the end. Okay, remember the number of bits that we require increase linearly with the number of states. Linearly is underlined. Okay, if number of states required to be generated is very large here, because this linear function dominates the logarithmic function. Remember this point, we will come to this point once again during the lecture. Now let us see quantum computing. So far we have seen classical computing and how bits are used to generate the states. Now let us see quantum computing. I said that the unit of information in quantum computing is a qubit. And what is the property of qubit? Qubit is a superposition of two states, state 0 and state 1. When I say superposition, what do? I multiply state 0 with a number alpha and I multiply state 1 with another number beta and I add both of them. This is superposition of state 0 and state 1. This we call as qubit. So this is used as unit of information. That means a qubit lives in two states at a time. Right? And we will see the details of alpha and beta later on. Now come to this point. One qubit will stay in two states at a time. What are those two states? Alpha 0 and 1. Alpha times 0 plus beta times 1. This is the state. For example, if you have two qubits, so you can generate 4 states at a time. Let us see this, how we get it. So for example, I have a qubit Q1 which is expanded as alpha 1 0 plus beta 1 1. I have another qubit, say for example Q2, and how is it written as alpha 2 ket 0 plus beta 2 ket 1. So what is the meaning of having two qubits, 2 qubits are expressed as tensor product. Okay, Q1 tensor product with Q2. So I have two particles, two qubits, one in state Q1, another in state Q2. Total state is tensor product of both the qubits. Now let us see how we do the tensor product here. See, Q1 is nothing but alpha 1 ket 0 plus beta 1 ket 1 tensor product alpha 2 ket 0 plus beta 2 ket 1. Now we see we do simple multiplication only. Alpha 1 alpha 2. Say for example alpha 1 alpha 2. This is ket 0 0. See, you call it, we write this as ket 0 0 plus alpha 1 beta 2 alpha 1 beta 2 ket 0 1 plus beta 1 alpha 2 beta 1 alpha 2 ket 1 0 plus beta 1 beta 2 ket 1 1. So I have 4 states with 2 qubits. All 4 states will be seen simultaneously. So I have 4 states with 4 states are generated using 2 qubits. If you continue like this, if you have 3 qubits, you can have 8 states at a time. These are all the 8 states. Simple mathematics will give you this answer. Now continue this. If I have n number of qubits, you will have 2 to the power of n states at a time. Right. Now see this one. How we are going to have a conclusion from this one. See, what is that? Number of qubits versus number of states generated. What is that I said? You have 2 to the power of n states generated. Let us see this one. 2 to the power of n states generated using n qubits. I have written the same thing. 2 to the power of n states generated using n number of qubits. Okay. Now, you take log on both sides. You will have n number of states at a time. Okay. With log n base 2 number of qubits. Right. Now, earlier in classical computing, if you want to have n number of states at a time, how many bits we require? Let us see this one. We require n log n base 2 number of bits we require if you want to generate n states simultaneously. But in classical quantum computing, n number of states you can generate using only log n base 2 number of qubits. So you don't have this n term here. In classical computing, you have this term. Log n log n base 2 number of bits you require. Whereas in quantum computing, you have only logarithmic function. Now you see the graphical representation. Number of states generated along x-axis, number of qubits that you want along y-axis. So if the number of states that you want increase, the number of qubits required increase only logarithmically. So now what is the conclusion from this one? Let us see this one now. Very, very powerful property we understood. Because of this superposition property used in generation of a qubit. What is that? Whatever n number of bits that are doing in classical computing, same thing that you get using only log n base 2 number of qubits in quantum computing. So that is, you are generating large number of states, right? You are generating large number of states using qubits. That is one point. And this is a linear problem. See that. What is that? A problem with linear complexity in classical computer is reduced to logarithmic complexity in quantum computer. So complexity is related to the number of steps that we require to solve the problem. So if a linear complexity problem is converted to logarithmic complexity, it is advantageous. Okay, you can quickly solve the problem. So this is the power of quantum computing. So also you are going to generate large number of states. Your state space is increasing. Increase of enhanced state space will allow you to find correct answers by using right quantum algorithms. This we are going to understand in forthcoming lectures. So the summary of the presentation is, superposition is a very powerful property that is used in quantum computing. A problem with linear complexity in classical computer is reduced to logarithmic complexity. So this is an advantage of using quantum computing. So thank you for listening to the lecture.